So good morning, everyone. I'm Jimin Zhao. I'm from University of Amsterdam. I'm assistant professor here, and also I'm a technical manager in the Lifewatch Virtual Lab Innovation Center in Amsterdam. This talk mainly is going to be given by me, together with two of my colleagues, one is Spiros and Ricardo. So they basically prepare the lab tutorial part. So they will also join the open discussion and also these lab support sessions. I think Thursday. So this is the second session we prepared for the cloud computing part. In summer, we had one webinar. We discussed the basic concepts of the of cloud computing and how the cloud works. So I don't think everyone were there, and even not sure everyone had time to watch this video. But I prepared like a few minutes, quick summary of what we discussed. So basically, for us, we are all scientists. Also, maybe some people from the data centers do the data management. So if you look at all the activities we perform every day, so basically it's a combination of many activities. For modeling, from the scientific point of view, you study data, you build simulations, and you try to understand the problems, write papers, publish it. And there are also colleagues who look at data life cycles, check the sensor data, curate it, make them accessible, publish them through catalogs. Also, we have colleagues, they manage the computing storage capacities, and so that they can support both scientists and data managers. So basically, this is kind of cycle continuous running, and they are actually, let's say, combined. It's very difficult to separate them. And sometimes scientists also have to do lots of, data cleaning, curate data content, check the quality before they can, pump them to their machine learning pipeline, for instance. These colleagues from data centers, when they manage these, the workloads in the computing facility, they also have to understand a little bit about workflows, how the behavior is. And specifically when, capacity running out, they can know, for instance, how to, better schedule different jobs. So when let's say, these kind of, scientific activities get bigger and bigger, we are facing many challenges. One of the, first challenges we're facing is the scaling challenges. Scientists always have bigger ambitions. They want to process more data. They want to integrate, more sources, more simulation models to tackle more challenging problems. But, how to get access to them, how to fit all of these in their, local computing capacities and do the job. So this is a problem they have to, face. And in the meantime, after certain, iterations, when the software quality becomes mature, they deployed it as a kind of, online service to serve the others. How to make sure that service has high quality with, low response time, so everyone can, access it, do the processing as, the user expected. So that kind of, quality issues also make these, activities very challenging. And more often, if you want to run certain jobs out of your own computer, do it in remote facilities, the migration is not easy. Basically, you have to, couple all the computing contexts, libraries, and make them in a self-contained package. But how to do that, and how do you make sure, the remote platform supports that? So all these issues, basically, we need new infrastructures. Big infrastructures is the, the fundamental thing to enable our big science. And cloud computing is one of the, let's say, new generation of these, infrastructure, give us different possibilities. And basically, these two lectures, we try to understand, how cloud computing changed the way, we develop and operate or execute our scientific programs. So I try to, make the talk or webinar in a way which we can tackle the, let's say, the kind of problems, real problems we're facing. I highlight two problems nowadays we're facing. One is more from, domain scientist point of view. For instance, if you have a code, if you want to run that in the cloud, what are the options and how do you make choice? Second is, the problem is, for our, let's say, research infrastructure developers, if you're making data management services and you want to operate it to serve your community, and what would be the best practice for you to, do the software engineering, and how to make use of cloud, to make the operation in high quality so that, the community can get the best benefit out of it. And also prepare some lab assignments, a tutorial to help you, practice some skills. Cloud computing is very big. It's very difficult to try all the technologies. But from those basic training or basic tutorial, we hope, you can get some kind of, insights on how cloud works and how to extend the technology we explain you during this webinar, and to extend that to the real situations you are facing. So I prepared a few slides just to give a very quick overview how cloud works. So if you need more information, details, check the previous record, which we did in last July. So about cloud computing. So all what you need to remember is cloud is basically everything about computing resources. They become a kind of services. What do you mean service? We will have actually a few slides later in the second part to explain what does it mean. But for the moment, just remember, service is kind of online accessible, let's say kind of products, which basically you can make use of remote resource in different ways. For instance, infrastructure part, we have computing capacities, CPUs and GPUs, all different cores, and storage networks. All these will become a kind of service. And we have the platforms, for instance, the database, it could be a platform, could be like a Jupyter environment that can also be seen as a platform, or a kind of web hosting, web server. They can all be seen as the the platforms. Now they also can be seen as a service, and software itself, like instead of installing the Microsoft on your own desktop, you can just use these through web. The software also becomes a service. So how actually you make these things as a service? Yeah, this is the first thing you need to understand. Basically, there are two technologies. Keep that in mind. So first, you have to understand how can people make a big machine, make it behave like many, smaller machines we are using through internet. So basically, these are the machines you see in the data center. These are racks, a collection of the many physical servers. But now here are the virtual machines. For many people, actually, when you're using virtual machines, I don't think you have a clue where those virtual machines, where are they from, how the physical server look like. Basically, you don't know, or you don't have to know. And second is, how can actually the cloud provider handle many users and in a kind of concurrent ways. So the technology one, keep in mind, that's virtualization. And this is a kind of technologies originally developed in the 1960s, but that time it's not completely different from nowadays, the virtual machine concept. But that time people already start to abstract the physical resource, make them as kind of unit, and people can use a portion of it and feel like they're using the complete environment alone. So that is a kind of technology in computer science already developed half century ago, and with many years development in around like 2000, actually people in the big companies start to invent technologies to encapsulate the entire computer as a kind of abstraction, so that we could make use of a physical machine in a way as a kind of software environment, and you feel like you have abstract of the of the hardware, software installation, operating systems, everything, just like a real machine. So that is called a virtual machine. This is not a real, it's a software, but it emulates the actual behavior of a physical machine. That is virtual machine. And it has the information of the hardware, physical machine, like physical machines, but it also has the software which you can customize on top. There is a magic software, keep that in mind, that is Hypervisor. So about the cloud, if you want to know technology, these are the few bullets you need to remember. Virtual machine, these are the kind of solutions, basically to partition the physical resource, isolate it for different users. And virtual machine images, these are the files stored in the computers. Usually they're very big. It could be several gigabytes. And if you load that in a system, that becomes virtual machine. Yeah, these are also two different things. Virtual machine images, they're dependent on this magic software I just mentioned, Hypervisor, which means you cannot say I have a virtual machine images. I run this on any the environment or any cloud. That's not possible. You have to first check if the hypervisor supports that. And one physical machine only run one hypervisor. So that's technology one. Technology two, remember, that is the orchestration. If you want to set up your own cloud for your infrastructure, basically, you have to, besides you have physical servers installed virtualization, you also have to, think about, you have many users, how to help them concurrently. Basically, you have to decide, many physical machines, when there is a request, where should I put this virtual machine? Here or here or there? There are many constraints like energy consumptions, like load balance performance. But there is a kind of system do this decision for you. That is called orchestration system. OpenStack, this example, CloudStack, vRealize. These are all things. Commercial companies like AWS, Azure, or from Microsoft, they have their own customized things. They're not open source, but more or less they do the same job. So usually they have user interface, one for the the end user, and the other types of interface from same system for the administrator. So basically for this, keep that in mind. Orchestration is interacting with the hypervisor, but this is not hypervisor itself, which means you can use the orchestration software like OpenStack, talk to different hypervisors at the same time. They can coexist, but orchestration itself, it's just management. They support, they give interface for both user and also the administrator. So if you know these two technologies, then cloud is not magic anymore. Because we can automate these virtual machines. Then you could think we can sell this as products, like what you buy things from eShop. You can check the catalogs and providers basically if they get your VM request based on your size, and then they provision it through these two technologies we just mentioned, and then you get the virtual machine, you use it, and afterwards you pay do the payment. With this technology, actually, the cloud can give us two important features. Actually, put them together as one feature. It's called elasticity. First, you could select different size. If you have a small size, you can make it big, which we call vertical scaling. And second is we call horizontal scaling, which means I have one server for one particular applications, but now I want to scale it out with many instances. I could simply ask cloud provider, give me those instances with same size. They could do this in a few seconds. So that is so-called horizontal scaling. Cloud, they are different. They have community cloud like EGI, like XG. So those are the things basically more for research communities, different organizations to come together, share the resource. Basically the resource only mainly serve their own people. That is called community cloud. And public ones, that's the one most of us, I think, heard about it, like Amazon, Google, Azure. And hybrid, it's a mix. Private ones, actually, it's the one. If you use these two technologies we just explained, actually, you could set one for yourself. Remember, actually, there was one European cloud white paper or strategic white paper published in 2019. In the near future, actually, let's say multi-cloud with secure hybrid business will be the trends. There are many reasons for the security reasons. For instance, for the data management, many countries more care about, or organizations care about their data accessibility. You don't want to put everything in cloud, but how to manage that, maybe part in public ways, public providers size, and the other party hold it in your own, private cloud. But once it's clear, almost all the IT infrastructures are moving towards cloud, which means they are all moving towards this virtualized way to manage their resource. That is for sure. So this is a very quick summary, but I still would like to know a little bit more about you. If you could just tell me a little bit about cloud service you're doing, and check this Mentimeter, type the code, or even scan this 2D barcode. Since we are running out of time, you could do this while I'm talking, but I want to have this information because that will help us better understand, in the technical part, how to help you and how to give you support. So go to the Mentimeter, try to type whatever service you have used. If you haven't used anything, that's also fine. Just type this in there. So I give stop here 1 minute, then we continue to the real discussion. And also you need to think a little bit about, maybe you're using something you're not aware that it's cloud service. For instance, you use this like storages, like a Dropbox. Actually, Dropbox is cloud service. It's storage service. This can also be seen as infrastructure service. Sometimes you're using a virtual machine for your development, but you get it from your own institute, and they don't call themselves cloud, but actually they are already it's a kind of cloud technologies, cloud instances or service instances in it. Very good. I saw a lot of people. Let me share the screen. Maybe you can all know each other, better. So we see people using, GitLab. GitLab is a good example. GitLab itself, of course, it's just software, but it's a kind of platform as service or software as service. Azure, AWS, good. EGI service. I think once it's good, we all have some kind of experience that can make the discussion quite easier. Good. Let's move back to the next part, that discussion on the first questions. Let me see where is my, yes, it's here, yes. Now let's do the first discussion. Yes, how to run a scientific application in cloud. Maybe you already tried it. For instance, I saw people have this experience with virtual machines from EGI or from AWS, but that's still refresh a bit. If you have a scientific code and if you want to run that in the cloud, what are the basic things you have to consider? There are many choices. I'm sure people use other choices, like you're using Jupyter. I saw that using Jupyter Hub from EGI probably. And some people use like a database service from cloud. But these are the basic three choices if you put it in a very rough way, infrastructure, platform, or software. But in fact, with these big providers, if you check their portfolio, the service catalog, they're glowing almost every day. There are all new items appended in their list. In the recent ones, you heard a lot. For instance, serverless computing. Everything as service, like blockchain becomes service. You can just take it and use it. And the software management platform like DevOps, it's also become a service in almost all the providers. So we're not going to discuss all of them, but we're going to focus just one basic one, infrastructure service. The reason for that is if you understand how infrastructure service work from both provider point of view and the user point of view, actually you could expand it in many different ways, to other types of services. So, but before you do, this kind of cloud execution of your application, you have to first understand what are the applications you are dealing with or you are developing. And they are all different. They have different characteristics. They are different. They have different, requirement on the computing, like CPU capacities, memory, and also, I/O and the networks. For instance, modeling and simulation, big data analytics, machine learning, they all have slightly different patterns on these characters. So this would be the second thing I want hear also a little bit more from you. Try to type a little bit more about the applications you are developing. Maybe it's one of them. I heard in the first lecture, when we introduced ourselves, some colleagues, some students says, okay, I'm doing this kind of modeling, from atmosphere size to the inverse modeling. That could be seen as more like a modeling simulation part. And in the Lifewatch, we also hear some kind of let's say the work you do, to combine different data sources to analyze them to build a machine learning pipeline to identify species. Or you can do this. You do the same in the data centers. Process these observation data, more like sensor data processing. Write a few words about what are the kind of applications you are developing, and so that we can also better understand the types of challenges you are facing. And if you're not, let's say, domain scientist, you don't develop any of them, but you more like operate some kind of services in cloud. For instance, you're maintaining databases for infrastructure. That's also fine. Just write this down with a little bit extra words about the challenges you're facing. That will be very helpful also for the later discussion. Very good. So I already see quite a lot of input here. On-demand module, run service. Yes, model run service and a sensor data processing workflow tasks. Very good. Automated data. That's good. Made the data catalogs. I was looking for actually a little something like the workflow. Let's say types of applications. Yes, we found a few of them. Very good. So I think the rest of these parts, before break, I would really like you be more interactive. If you have any questions, feel free just either type it in the chat box or raise your hand or just unmute yourself I think, more interactions is always helpful. Let me get back to these slides, and then, we're going to explain a little bit about these, technologies there, and then you can check what are the technologies you're already trying, and maybe you have better practices. You can also share that with us. I pick one of the examples from Lifewatch, which is the one actually we developed now recently with a group in the University of Amsterdam. So they basically develop a kind of scientific code to process these LIDAR data. LIDAR data is kind of light detection and ranging, measurements. So you got a lot of, raw data from these, airborne laser scans. In the Netherlands, that basically, every few years they do one scan of that. There are lots of raw data, and the students, basically it's PhD students, and that student basically did the pipeline and to process it in Python in her notebook. So basically these are the steps. You load the raw data, and then you do the retrieving, and then you do normalization, and extract the metrics. At the end, you do the rasterization. So, by the way, first you have to know, I'm not an ecologist, so lots of detailed knowledge about how the workflow works. Probably I cannot answer that, but I can explain you how did we help her, migrate those things, scale this out, and then do the computation in cloud. So basically, the reason, we start this small project with her is, she tried to expand these data sets. She originally processed only for a region in the Netherlands to the entire country, and then moved towards, all the other countries in Europe. So that's typically, I think, the first motivation for lots of us. And then secondly, also would like to, to increase the model a little bit and try to see if we can combine different data sources with different models and to make the, processing, make the prediction, more advanced. So for this action, actually recently, we even, tried this and get a small project from Azure, to do this, this European scale LIDAR data processing. And then this basically the key motivations, I think, I'm sure lots of you, perfectly understand this, you're facing that. If you look at 10 years ago, 10 years ago when scientists, specifically researchers, facing these issues, when they're facing, capacity is limited, storage is small, CPU is small, you could do two things. One is, be more active. You just think about how to, extend this using all kinds of technologies like a parallelization, do computation in different tasks, different programs, or, you try to optimize everything, in the computation, make it more efficient. That is one way. You can also actually do nothing, because if you look at 10 years ago or even a little bit earlier, from the, let's say, 1980s, basically computing capacity really grows very fast, and these trends basically it continues until the time more or less, let's say, around 2005, and that becomes a kind of situation. All of us have to face the situation. If you wait for the growth of the natural growth of the computing capacity, will not work anymore because of the the engineering aspect, engineering challenges or boundaries for building those chips. Energy is one of these issues, and it's through the computer itself start to hit all kinds of limits, the memory limits, the power limits, etc. We have to, basically all of us have to think about, in a computer where almost all the laptops, we have multiple, CPUs or multiple cores, and how to, make use of this in a maximized way. Can we, distribute the tasks, either make the multi-threads or make this as multi-processes? So that is the first thing we have to, we can think about. And that actually already reflects in lots of your code. So that is the thing you have to first understand when you want to run this in cloud. What's the special techniques you applied. And if you want to run this kind of parallel code, or this kind of standalone application, now doesn't matter if it's parallel or sequential. If you want to run in remote ways, there are already technologies for doing that. Also, a long time ago, almost half century ago, because we have remote computing centers. We have these, we call these computing clusters. These are the facilities I think lots of us interact with. Basically, the way you do that is, you send code there, and you have to recompile the code, and then you use the job submission systems, execute there. The advantage is, you can always know lots of hardware, special hardware in advance. For instance, if you need a GPU, if the remote infrastructure provides that, and you're excited and you tune the code, you compile there, and you can really make the throughput very big. But the bad thing is, of course, that environment itself, usually it's shared environment, and you don't really get complete isolation of the performance. And second is, because the resource is limited, you can wait and for a long time. But also on the other hand, the code has very low, portability because it's so bound to a specific infrastructure. So for cloud, this basically the cycle we just explained will be changed. So the infrastructure is not fixed anymore. You can program the infrastructure by actually customized based on workloads. Yeah. So that would be the first step if you think about using cloud. Second is, when you plan infrastructure, you decide how many VMs you need, and then you have to, you can do the second step, that is provisioning. Provisioning is the one, if you remember in the, in the first part, there is orchestration, there is hypervisor, these technologies. Basically, you're invoking them to get it provisioned. Then they will become accessible. The third step is the deployment. Yeah, you deploy all the platforms, software, and last one, you do the monitoring and execution. So actually the steps are very straightforward. And if you look at almost all the applications, and more or less, you can always basically, specify in these 4 steps. Sometimes you combine them, like what we're going to see in the next few slides. What we're going to do first, quickly go through these, the steps, specifically the first step a bit, explain what are the things you need to consider. So the application characteristics, that's the first thing. Programming model, it is, the sense. If you do the sequential code, that's more or less simple, isn't it? You assume there is only one CPU, and you follow in this kind of, Turing machine models. Instructions are sequentially executed. But the parallel code, that is a bit different. If you're using multi-thread, multi-thread, of course, can only bring you benefits if there are more, processors or more CPUs available. If you only have one single CPUs and you have many, threads, basically the performance will not really improve because they all have to, execute, wait for the same CPU to do the job. And the MPI same, MPI is the message passing interface. You have different, instead of threads, and you have processors. The difference, I think you know that process are the ones, they have their own independent access to the memory. Threads, they have the shared a bunch of shared memory across them. And nowadays we talk a lot about the CUDA and the GPUs. This can be seen as kind of many cores. Each GPU basically has a kind of processor. It's not like CPU cores, but they can do certain jobs, very simple ones, but they can do massive things because there are many cores in the GPU, kind of board there. And that's one type of the workload you may have and you need to think of. And the second is the workflows. Workflow, it's a kind of, let's say, list of the dependencies, dependent tasks. They have input-output dependent, and there could be the short tasks for computation. There could also be services be in the memory for a really long time. And you also need to know what's the communication characteristics. Is your application driven by the big files, or is it driven by the small events? Yeah, the difference is, big files, usually they are big, streams. They need lots of, network bandwidths. They are, we call this, relevant traffic in the network. And the events, they also could be a lot. They can also consume lots of bandwidth, but they are small messages. They don't have to, use the big chunk of the bandwidth, but they can be the smaller fragments. And the last is, of course, computing tasks. We already mentioned it's a short life, or it is, long durations. Because for a short time, you can combine them, cluster them, put them in the same virtual machines. But if the persistent services, then you cannot do that. Because if you do that, then the performance will be low. With all this, basically those are the aspects you need to consider: the CPU capacity or GPU capacities. Nowadays in cloud, GPU is not really common, but some big providers can already do that. If you check Azure and also AWS, there are some data centers offer GPUs. And in EOS, in EGI, there are also these, Jupyter Hub. They also can offer you this GPU capacity, but you need to negotiate with them in advance. Yeah, the second one's communication part is more related to, what types of the, IO or network capacity you need to request. The last one, it is more for you to decide the, how to cluster, the different parts of your applications. So the planning itself has to consider, these types, capacity, topology, but more importantly, the price. Yes, but we're going to see, how do you normally calculate price. So this is a very brief analysis, about these, different characteristics. You could do the same thing about yourself, but remember, this is really a kind of, a very brief analysis, because all these applications are really specific. If you, it's application specific. Same simulation, it could have complete different characteristics in the memory or in terms of the CPUs. But if we say you do these simulations on like fluid dynamics and using a kind of, parallel simulations, then you would see similar kind of, patterns in terms of the memory and also the CPUs. And this is the tool nowadays the public providers often offer you. This is the so-called calculator. You could use this calculator, and based on your estimations, and you choose the types of operating systems and the kind of purpose of your virtual machines, and then see the price for specific number of cores, and then size of the memories, size of disks, and also the bandwidth, I/O, throughput. And then the system basically, the provider usually give you a kind of estimation of the price based on how much time you need. Typically, the providers give you a kind of quote on the price in like per hour, and that means you can stop it at any time, and then you only pay the amount of the cost when you use it. If you don't use it, then you don't have to pay for that. And if you really need a VM for a long time, for instance 1 year or 2 years, then what you can do is you can make a kind of reserved way to get the VMs. Then the price can drop dramatically, and maximum could be like 30, even 40%. Yeah. So now let's get back to the second part, these workflows. Running a workflow in cloud, it's a bit more complex than run a single standalone applications, because they have many tasks. And if this workflow is based on services, for instance, this is a flow. I have 5 services here. And all of them needs a kind of, let's say, stable quality to serve their communities. Typical ways, of course, you could just allocate 1 VM per service. And this actually is a practice we often try in the early years. And that's the early years when what do I mean is, before Kubernetes or Docker containers become popular. That was the practice we often, we often do. There are also research in the computer science communities to investigate how to, put service together and do these, schedulings. But this changed a lot when Kubernetes, when Docker become popular in the cloud world. And what you can do is for the service workflows, you could just estimate the total capacities and then look at the, the number of cores and the memories the biggest service would can consume, and you use that as a kind of basis. You request a couple of VMs which more or less reaches the total capacity, and make a cluster there, and then deploy these Docker cluster plus its orchestration software, which is often ones like Kubernetes or Swarm, and then manage the deployment of the service for you. In that way, actually, the deployment of the workflow can be much easier. And remember once, if the user of the service can be very big, be aware you have to always reserve a little bit extra resource to make sure the cluster has extra capacity to this auto scaling. So that's the type 1, which is let's say the simple ones, which we call the workflow of the services. But the second ones, is about what about if you have a workflow with lots of small duration computing tasks, which is also have the similar patterns like this. Have a bunch of tasks, they have dependencies, and then one task can only start when the previous one finished, and they connects or communicates based on the files. The first one, like this one, finished, and the generated output could be the file used as input for the next ones, and next one finished, generate input for the one afterwards, and continue until the last one. So there are basically 2 ways to do this kind of workflow in cloud. One way is you could just do this in the on-demand way. on-demand means, you don't really care how many workflow, how many tasks left. You just check at the current stage how many of the tasks you can execute, and pick the ones you can execute, and then check for those tasks what are the virtual machines which you can get from the provider, and if there is capacity, and then just execute it. And that is the which we call on-demand ways. And if you check the literature actually from computer science world, and there are lots of work about it, because this is a typical way to make use of these cloud elasticity. And very often at the end, for this complex workflow, we probably only need one virtual machines, because always the next task starts when the previous is finished. You don't really need a lot. Maximum you probably need one extra, because you have parallel tasks. Yeah, this is a kind of typical way. But sometimes, there is another one. I already take the slides out, it's too much, but I can explain you here. There are also some kind of workflows which have a very specific requirements on the performance. For instance, in the data in research infrastructures, if you want to have some kind of real-time support for a workflow, for instance, I want this entire workflow finished within certain time duration. If that is the kind of task or workflow you have to deal with, and using this way, sometimes it's not enough. And there are also technology to do that. You can make a plan for all the tasks based on their earliest starting time, latest starting time, to calculate what's the total number of VMs you need to reserve, and then make all the VMs provisioning in advance, and then make these scheduling there. So if you check our this ENVRI book, there is a chapter actually we talked about this. We applied this technology in the Uruguay, in the marine community, to help them process their data subscription services. It's quite interesting. If you have time, I encourage you take a look there. Yes. And the second stage, if you know how many virtual machines you're going to need, and then you can specify all these virtual machines, any kind of descriptions, and then automate the provisioning. Either if your virtual machines are all getting from the same provider, the provider itself normally give you the API from their orchestration service. There you can just give the specification, they do the job for you. But if you're dealing with different providers at the same time, so usually you need a third-party automation engine. There is one actually we developed in the ENVRI Plus project, and it's called a dynamic real-time infrastructure planner. This is also a kind of technology we have further explanation in that book, in the chapter of these data subscription service chapter. Take a look there. You can understand, for instance, in the cloud ecosystem, if you stand as a kind of a broker across different provider, how can you automate those provision? So this part we'll not discuss too much here. And by the way, in EOS they also have similar solutions for there. From Indigo project. So the deployment. Yes, so the deployment, it's if you look at the deployment from the very classical way, which means you're only dealing with software code, then what you normally do is when the VMs get there, and what you receive from the administrator is just a username, password, and an IP address. That basically from there, you just get an empty system. Empty system means you only get an operating system like Ubuntu, and you have to log in it and install the platforms, libraries, and then get the code there. Check if you have all these compilers. If you're using Python, then you have to check all the Python libraries there or not. And most likely, you can manually fix it if you know how to do this locally. But of course, if the system is very big, which means the workflow, if it's big, this can be very time consuming. There are technologies to help you, for instance, using these Ansible technologies to automate the deployment. There was some tutorial we mentioned, actually we discussed in the previous lecture in July about it. So you can try that. And it's also used by lots of framework to do this automated deployment. But for domain scientists, I would say, you still feel it's too much for you, because you don't want to touch these things. You just want to focus on your code, and you just want to run the code in from your small computer as a laptop, bigger ones, get your results, isn't it? Why should you know all these details? That's why there is another way. You have to know how to encapsulate your code, to to couple, all these, runtime information, libraries, environment. Can we put them as a kind of self-contained environment so that I can just take this encapsulated package and move to the new computer environment and unpack it and run that? And of course, you can do that. There are 3 options for you. Option 1, we already mentioned, virtual machine images. That's a way. Actually, in the few years ago, it's still very, very popular. Even nowadays, for the big systems. For instance, there was a system we are trying in ENVRI that is called Open Semantic Search. If you check their website, actually, they basically pack everything. You get as a VM images. You get it, and then you deploy that on your own environment through like a virtual box. You get everything, configured. That's one way. The idea is, if you use virtual machine images and you get basically application platforms, file systems, operating systems, hardware characteristics, everything zipped together. It's just file. If you know the VM standards, you can more or less, open the file and find it out, what are the information there, how they are structured. Second one is the container technologies. Container technologies, it's a bit lighter. And the difference is, it has application information, has platform library information, also file systems. But remember, operating system part, they don't have entire operating system. They only have these, operating system libraries, and very small part, very light. The kernel part, they left it because they think, the environment, the system should provide it. And the third option, if you're dealing with Java applications, really a lot. For instance, you can make a Java file, pack everything, in a relatively small ones. But the thing is, if you packed it as Java file, it can only be run in the kind of environment where there is a Java virtual machine, isn't it? So for each of these 3 options, of course, there are other options that are more in the classical ways. For instance, using these bundle technologies and then make installations, files for certain things. But we're not going to discuss them, because that is for the cloud world. This doesn't really bring much new, let's say issues or innovations there. For these reasons, you have to when you make a choice, you need to understand a little bit of their limits. So the VM images, they are just first, they're big. Second, also need to understand they are they can deploy. They need a specific hypervisor deployed, which means you cannot really bring it to anywhere you want. For the Docker containers, the minimum requirement, if you have a container images, it needs the Docker engine from a system installed and to interpret this image. And it also requires the system has an operating system kernel there, which means these 2 things in principle have to be compatible. Usually the systems, if you run a Docker, the Docker engine actually checks, your description file, and they actually recompile these images in real time to make sure, the libraries are compatible with these, the kernel of the operating systems. And the rest, the VM, the hardware part, they all left out. And then, but for the third options, of course, has a little bit more requirement on the runtime system. The practice shows, in the cloud, basically, this becomes really the trends. There are not so many things, to argue about because the industry pick it, and also it has many advantages. It's lighter, it's faster, but it also has lots of, criticize about Docker containers. Early years, the main criticize is about security because it doesn't really have a full isolation between these users, between processes. So the Docker, I will just move a little bit quicker. Let's have breaks in about 10 minutes because we start a bit late. Is that okay? Yeah. If you want to have break earlier, just write a message in the chat box. Otherwise, I just continue. So the Docker, how it works? It works like this. If you have, this is you, the client, and this is a machine, and there is a Docker engine. This is a minimum thing you have to install there. And then the system, this is a memory part. It's containers. Now it's empty. Nothing in the memory. And this is, the images. This is in the file system of that particular computer. You can see some images already there. So if the client says, I want to deploy a Docker, and this is my, Docker file, description file. I want the image, it's MySQL, and the volume, and then, the environment, et cetera, et cetera. Basically, you can specify all the things you need for that particular Docker. And then the Docker engine first do one thing, it check, in the local files, is this image exist or not? If yes, and then, just take it and then deploy that in the memory. That becomes a runtime systems, and you can access it. And in other cases, for instance, if you access it, the same images, but if you look at system, there is no, this, MySQL there. What does it do? The Docker engine actually, start to contact a remote repositories. Typically, by default, they will contact Docker Hub, and then check the images which you specify in this file is if that one exists or not. If yes, and the engine will fetch it from the remote repositories and download that to the local system. And after download, and then to load it and make it as a, let's say, running instance. And that is another option. Yeah. And as I said, in the big providers in industry, this Docker becomes really a trend. And there are different management systems like Kubernetes and Swarm and Mesos. And this becomes a kind of, really fast growing, these community build these management systems to handle how to manage the Docker in a large scale. Basically, all these software do one type of things. Is they can make a couple of machines, as a cluster, and each machine they all have a Docker engine installed, but then they have one extra layer through that management software that talk to each other to understand the load of each machine. This is example of the Kubernetes. And if there is a request, and these Kubernetes management software start to decide what is the best host to deploy those containers. And they provide one extra layer. Yeah, you can group those containers in a kind of small group which called a pod, so that within a pod, these containers have better way to interact. They can share storage or network. Yeah, and in this way, if you have a workflow, actually it becomes rather easier, isn't it? You could wrap each task of your workflow as a container, and then throw that to a cluster of the Docker. And the job actually becomes, much simpler than, in the classical world. So now let's wrap up, see what are the options we discussed. So option one, we explained, that's the one, we just discussed. You plan a virtual infrastructure, decide how many VMs, and the provision of VMs, and you Dockerize your scientific code and deploy the containers on a Docker cluster. And this, I would say, it's a kind of standard or classical ways, for you to run almost any application. If you followed it, more or less, you can run any application in cloud. But you can always, simplify it a bit, because, planar infrastructure sometimes takes time. A simple way is, of course, you get this. This is more, take a bit of reverse. Instead of using Docker, you could just, get the VMs and provision it, but you don't use any Dockers there, and you just directly deploy software. It can be customized, make more efficient, because sometimes the performance, you can gain a bit of performance there. But the thing is, these clusters sometimes have more issues about, about the scalability, because you will start to, customize lots of libraries across them. So more often, actually, people choose these directions. You just start from containerize your code, but you don't request any virtual machines, because this you think is just too low level, and you don't want to do that. The thing is, cloud providers nowadays, they can directly offer you a Docker cluster. They give you Kubernetes environment. You can use their Kubernetes environment to deploy your Docker. But of course, be aware, not all the providers offer that. But if they offered it, I think this can be a better choice. And the last one is, of course, if you think, even make a Docker is too much for you, and you could just use these platform as services. For instance, in this case, choose these like a Jupyter Hub and directly run the code there. Because behind the Jupyter Hub, they have their own cloud solutions. Usually what they do is, they deploy the Jupyter Hub itself as a kind of container on the container cluster. If the instance of this particular notebook you're running needs more memory, needs more resource, they can scale your resource out for you. But again, this is not offered by all providers. But if you want to start quick, big providers like EOS, of course, has it, and Azure also has it. and Amazon also has it. You know, it can do these big, you know, even have lots of customer libraries for doing machine learning. So, but also you have to be aware one limit of this approach is, you know, if you only focus on the notebook itself, because in the ENVRI community, notebook really get lots of, you know, attention. Scientists are really produce lots of notebooks. But the thing is, you know, if you want to take somebody's notebook, you say, hey, and this guy really did interesting work. I want to take that, you know, content as part of my workflow and extend it to do some big, you know, experiment. And you will find actually that's not really straightforward. There are some solutions to couple different notebooks, of course. Yeah, you can also manually copy this, you know, content of the notebooks, you know, in one single big notebook. But these all, you know, are kind of, you know, dirty things. Not everyone want to do that. Can we think of something, you know, even for notebooks? Can we get the content, make the Docker, and, you know, make this as part of the workflow much easier or simpler? So that actually, you know, is something I want to, you know, use a few minutes to explain, discuss with you, to see in the Lifewatch, how did we, you know, bridge that gap? If notebook, for instance, this is the one you see. This actually is the example I just explained from the college. The student code for that, you know, leader data, it's already there. It's open source. We take it. But the thing is, you know, if we want to make a workflow, we don't want to take every part as a workflow. Maybe some part is, you know, more reusable, and we need, you know, scale this out. The other parts, you know, it's a sense, you know, even you scale it, it doesn't really gain anything. You would like just keep these things as it is. So the question becomes, can we take a segment of the code, basically in the Jupyter terminology, it's typically the cell. Can we take it and make it as a REST service, and then encapsulate it as a Docker? Because if we do it in this way, I could, you know, or we could put that in the cloud, deploy it anywhere you want, and then make it as part of a workflow, isn't it? Sounds very logical, isn't it? So basically, the flow is like this. We take these things, and then we generate a web API and containerize it or Dockerize it, and then to the cloud. So basically, you know, all these things now, you know, has been prototyped and actually been tested also with this ecology, you know, scenario. It's open source, and we take actually this as an example, make it as a lab tutorial. We encourage you take a look and try the same code we did with the ecologist and see how these, you know, how these workflow look like. Because from that environment, you can get some kind of knowledge about, you know, how the Docker file look like. How normally do you compile a Docker file to generate Docker? And how do you, you know, load the Docker in a remote environment to execute it? So basically, those are the things you can try from this, you know, tutorial. And this is the, you know, the snapshot of this, the software we call Fairsail. It is a kind of extension of the Jupyter. If you follow the, you know, the link here, install that. Basically, you know, in a Jupyter notebook, you get one small button there, and that is, you know, we call Fairsail. You click it, and then you can start to select which cell of your code, and then the system start to, you know, to pop up a window, which is here, and then based on the code, we analyze what are the types of input, you know, the code, the cell needs, and then give you a kind of list. You can decide, do you want to make these, you know, variables as part of your API? If yes, and then you choose it, and then, you know, you generate this. The tool will generate these Docker file for you, and if you compile that, and then you get your Docker images, and of course you can, you know, you can publish the Docker you generated to the Docker Hub, to a remote repository. Then everyone from the internet, they can, you know, retrieve that, make a reuse of it. Yeah, that's one of the motivation why, you know, we do that. Try to enhance the current notebook environment with a bit better, you know, sharing on the code. That's also why we call this, you know, FAIR. You know, FAIR is now the sense, you know, for not only data, but also for any, you know, digital objects, research assets. So yeah, these are the two tutorials we prepared. The first is, you know, try this code, understand the Dockerization, how the basic steps are, you know, and check how these, you know, steps to publish a Docker to the Docker Hub. And the second is, you know, try to follow this second tutorial to install a kind of Kubernetes environment. And actually we choose a software called a Mini Kuber. Yeah, install that. And then, if you follow these steps, you can also load the same Docker you just created and see how that works in this Docker environment. And you're going to get access to a virtual machine provided by Lifewatch. Test it. Yes. So I think we're going to stop here for a break. Because we started a bit late, I think let me propose 5 minutes break. Is that okay? We come back 10:15. Is it okay? I don't hear anything. I suppose you agree. So let's have a break.
Okay.
Yeah, let's come back 10:15 and then we continue the discussion. Thanks. So before the break, actually, we stopped at this, the tool called Fairseer. And there we basically, in the first part, we discussed the basic technologies in cloud. We spent a few minutes on that. And then we also reviewed, different options for running a scientific application in cloud and what are the options. And also expand one of the tool we developed in the context of Lifewatch and ENVRI. Actually, that's also in the context of the US early adopter program. So actually, I would like to, before we move to the next part, I want to spend just a few minutes to show you a bit on how these things look like. Let's see here. This is the kind of demo we deployed. So this is the link. Actually, this is the, if you remember this IP address, you could also try to do this by yourself. So basically, this is the that little button I was explaining. If you follow the instruction, you can also install this by yourself. Let's see where, yeah. If you go to this, Fairseer from this pypi.org, you can fetch it, install this by yourself. And what actually how this look like is, if you click this, basically you get an interface. And there you could start to select which cell in the notebook. Basically you choose different cell, you get different ones. Of course, you don't want, you want to make some selections, isn't it? The relevant ones. For instance, if we select this first, the second one here, yeah, this is a piece of the code. And then, these are the input. This is kind of, interface which the system extracted from the code. You could define 3 options. You could disable it, which means, this will be the variable, basically the system will neglect it. And if you say the post, that will become a kind of, options in the defining the API. Then, based on REST, the conventions, we could define it as, input or output. If you don't provide anything, and then by default, the system will retrieve that from the code in the notebook. And you could generate these Docker files here. And if you get the Docker files, and then you can build it. If you build it, it takes a bit of time. We're not going to wait for that. It can take, a few minutes even. Basically, what it does is, to take these base images. This is the base image, data science notebook image as a basis, and plus this code which you selected and generate a Docker file. And if this is finished, you could test it locally. If you click the run, here, there is a port number. And if you run that, basically that service will be deployed with this portal on that same machine, this one. And you can open this on another, tab, type this IP address with this port number. You can change the port number to anyone which the system supports. Then basically you get these, deployed REST service for that particular cell. So that's more or less this little software do for you. And there is a publishing part. Here you can basically, decide where are you going to publish these images you just created. But you need a username password. because this is a third-party repository. We are actually now discussing internally with Lifewatch catalog colleagues to see if we can also make this part a little bit rich. For instance, use the metadata we just discussed yesterday, make this as part of the tab to describe the container and the surface, and then publish to the community catalogs like Lifewatch. It can also be other ones if you're from different communities. Yes, so these are the quick things I would like to share. Basically, the lab tutorial is more or less the steps. We give you more explanation how to do this, by yourself. Now let me move back to the presentation. We continue the discussion on the other parts. In the meantime, I see 2 chats here. Right, okay. Let's continue to the third question. Actually, it's a second question. It's how to develop and operate a scientific software in cloud. Basically, this is more suitable for the backgrounds. If you are a data management service developer, or if you are operator in the data centers. Yeah. We want to discuss three specific topics with you. The first is, why do we need a kind of, agile software engineering methods? And why do we need a kind of continuous integration deployment pipeline, for managing your software? So that is something, we first want to discuss. And then, we want to also explain you what is DevOps. And this term, if you are, if you read some kind of internet blogs or, check software industry, some kind of, white papers, you see these keywords appear very often, DevOps. So what actually does it mean? Why it is relevant here? Is that going to change, for instance, our daily activities? For instance, in ENVRI, we have many developers. Also, a lot of you are doing this kind of job for your data centers, isn't it? What, this kind of methods or practice can help you there. And then the last thing is, we also would like to discuss, if you want to set up this kind of framework for yourself in cloud, of course, we want to only focus on the open source part. There are commercial solutions that is outside of this lecture, but open source part, what will be the technology you can consider and how to do this configuration, how to set up it and how to use it. So basically, these are the 3 questions, we would like to answer during this, next part of this lecture. Again, as I said, be interactive. If you have questions, feel free to interrupt me. I will also try to stop during my talk, at these in between each of questions, so that you can have some time to ask. So let's start from one basic scenarios. If you are a software developer and you made some kind of software and you start to deliver this to your community, to deliver the value of it. So what are the typical ways, if you look at software engineering or software industry, how the people did that? So the first scenario is very simple, which actually still very popular in the open source community, which we call this code level delivery. You made a code, you publish the code in a GitHub or GitLab or Bitbucket, wherever you want. So you are only responsible here in the code. And then the user actually have to, fetch your code, compile your code, set up an environment based on your instruction. If if you're nice, you provide it. Otherwise, they have to figure it out, and then they have to do the deployment and installation. Finally, they can use. That is one way to deliver the value. For the developer, it's fine. If you are the developer, you normally like these ways. But I'm more general. I think lots of users are not developers, and the other way is like what we discussed in the previous session, previous part, that is using Dockers. You give the code, you develop the code, and you also encapsulate libraries, make this as a Docker container or images, whatever. And then the user basically take your packed things and then deploy it on their own environment. They have to find the hypervisor, or they have to find the Docker machines for your things, and then eventually they start to use. That's also kind of typical ways. If you check lots of, let's say a kind of sharing or collaborations between the community users, specifically in the workflow world, it's very common. You just download the Dockers and then you run it by yourself. But more often, especially if you look at the infrastructure, or if you look at the software industry itself, so actually more often people do these the service level value delivery. And so they give the code and then the library, but they don't want to, make you bothered about all these low-level details. They deployed it using their own machine, make it as a service. As a user, basically you just use it based on the API provided by the service, which normally is called a contract of that service. So this basically becomes a kind of trend in the software engineering. And then the service, of course, has many different definitions. Most of us think service like this. This is service because we heard about web service, we heard about REST, and we heard about web API. Typically like this, we have an online function and like a search function, it's a kind of service. And I'm here, I'm the user, and I can send a request based on the interface, give the keywords, and I return a list, return the list of the results. And then I make a selection of what are the particular item I want, and then system retrieve the content, return that to me. So that's a typical service most of us had in mind, isn't it? But actually service is much broader than this. If you only think about this, this is only the IT aspects of the service. It's only for you to do this management, of the invocations. And if you talk to the people, for instance, from the research infrastructure communities and with different colleagues in the meetings, you will find actually services are used in many contexts. For instance, you can hear people say, there is an organization offer long-term data archiving services. And they say, I'm running an application using cloud infrastructure services and infrastructure over supporting services, or training services. And of course, more often you have web workflow, invokes online web service. They are all called service, but their meaning are different. Why it is, why we want to start from all this discussion? Because, we have to figure it out with these different meaning of the service, which part actually, matters whom, and why this is the sense, as a operator of the data center, as an operator of certain service, why we should understand which part is very sensitive. So let's briefly take a look how this terminology evolves in the past years. So one dimension where the service terminology is from the software engineering, more from the modeling aspects. From modeling aspects, is if you in the 1970s, when people start aware, the engineering of the software, it is as it's a kind of discipline. We have to really understand the complexities, and then we have to really know how to structure the code. At that time, the different paradigms were invented, like structured programming. And then 1980s, we have object-oriented programming. And then 90s, people talk about distributed objects and using a framework like a COBA. And then the more fancy ones using agent or component-oriented modeling. We even try to encapsulate more stuff in the components, like even decisions. And after 2000, service-oriented methods of modeling, becomes a trend for industry, because there, has a very good implication how the collaboration between the industry parties should work together. And more often, or more recently, that microservice actually becomes a kind of discussion in the cloud, because the granularity of the service actually really make the scalability of the service, let's say, make that scalability different. If you have the granularity more suitable, you can scale it out much easier. Otherwise, it can be very low efficient. So another way is soon after the from software engineering, we end up with services. Actually, there is in the meantime, from the industry part, people are facing another complexity that is between different companies, if they want to do the online collaborations, and how to make one company finish their own process of certain business objective with help from the others. For instance, if you look at even our research infrastructure context, this is a typical business process. It's a data life cycles. There is a census, and the process starts from collect raw data and do the quality check, and then annotate the data content and a process generate data products. Finally, we catalog it and publish it. It is a typical process you can find in almost all data infrastructures in ENVRI and in these environmental earth science communities. But if you take a close look, this process actually it's not going to be done by a single person. It's going to be done actually by multiple persons from different organizations, isn't it? Data quality check, annotations, and then data product generator. They are all probably from different parties, and they offer different expertise and to make this process work. So which means, how can we make this collaboration between different parties in an automated way so that I don't have to send an email all the time to inform, my next person to say, hi, the data is ready. Can you check it and send an email back to me about the results? Yeah, this takes, longer time and sometimes, get delayed. The ideal way is if I make all my data ready, can I just let the system notify the next one and let the next one automatically respond to that and send the results back to me or to the one after him or her. So that is kind of, a motivation at the time when service-oriented computing was a kind of, a start to boom. And there, business process automation becomes a very hot topic in the early 2000s. There were lots of work, started. At the same time, actually, if you look at computer science, in the e-science, scientific workflow also get very popular in the same period of time in 2000. So that actually all contributed one final view of the service. Because if you look at the the business process, what do you mean? If the business process failed, what the implication is? Basically, the entire value is lost. Certain people collect the raw data. At the end, this raw data never end up with the products in certain catalogs. It just disappeared, isn't it? Then we lose the business value. If the process is successfully finished, which means that business value is delivered, and that actually is the more fundamental, let's say, implication of the service. Service actually, it is kind of intangible goods. It's kind of since you offer to the other party, and you use these kind of intangible goods to attract your customer, show your value, and then build your own market. So that is a kind of business meaning, and this meaning actually triggers the software engineering and IT aspects from the service. In many cases, if you're a developer, you often think in a different way. You think, I developed web service, that's why I create a business value. That's actually only partially correct. The real way, to implement value is not by the technology. It's actually about the way you operate it, the quality, and then also about the, how available your service is. So the business value requires high quality and continuous operation of certain sense. And that kind of sense, is normally implemented by software, which is implemented by, service-oriented architecture or other types of technologies. Why we need to identify these two things? First, we need to set some kind of structure in mind. If you are the, the developer for data management service for infrastructure, you have to keep one thing in mind: business value. What is the value for doing certain things? If there is something, your user, your customer, your community needs, that is your business value. You have to keep that as the highest, prioritized, goal. And from there, you understand what needs from the user, what needs from the community, and then try to bring this back to your developer on the back, in the back office, to tell them, look, this is what the community needs, and they need it only for this period of time. They are very urgent. If we don't offer it, they will run away. They will use the other people's service. So there is a very important meaning here. This agile needs to be quick. You tell the developers, and the developers start to respond to that, make the software, make the the implementation, and deliver that back to the the community, to the user, in a way is in a continuous way, which means you cannot wait lately the user wait like several months before the feature is released. You have to be quick. If you look at the big IT companies like Facebook, these kind of big internet companies, their delivery per day can be in the scale of the 1,000. Every day like 2,000 to 3,000 release, and these kind of deployment happened. And the big teams, on the back office, there are many teams actually. They work, collaboratively, and they respond to all kinds of, requests get from the, the operation side. And that is basically the structure why we think, the software development and then the service operation, these two things has to be coupled together, has to be continuously connected. And that is basically the meaning of DevOps. Yeah, and which is different from the way we thought about software engineering 5 or 10 years ago. Yeah, the idea is, you have the dev part, you have the code, you have build, you have testing, and that's the development part. Usually developers are responsible for that. But then you have the release, deploy, operate, monitor, and then give the feedback. That's the operator side. We need this, in this model, we need the developers more aware of this side. Yeah, aware of the business implication, aware of the operation constraints, understand the business needs. But on the other hand, you also have to make sure, you can work closely with the real user through certain gateway, role in your team. So look a bit back about software engineering. I know this topic probably, for lots of you, it's a little bit far away. You're not really, the professional developers, but understand a little bit about, how the things evolves can help you a lot, especially in a big project. If you are part of, a big development teams, you can understand why lots of, tasks are defined in that way. So I go a little bit quick, but if you think, it's too boring, I can even go a bit quicker. So the first model, we tried to develop software. It's called a waterfall model in 1970s. There, still lots of projects followed it. You have activities called, these feasibility studies, and collect requirements, analyze requirements, make the design, do the testing, basically step by step, sequentially. And usually, 4 years time or 3 years time, you made a software. The problem is very obvious. If you made small mistakes here, it can happen is after 1 year, you find it out. That's too late. And you run out of time, you run out of your money, and you cannot fix it anymore, especially for the, big projects, like ENVRI or ENVRI. We have lots of, data management services. If you follow this model, you can clearly see the risk. So instead, there is another way. In 1990s, people invented an alternative that is called V-shaped models. One way they want to reduce the risk is to do the testing all the time. For instance, if you make some kind of, this side is still more or less okay. Yeah, you do the requirement, you do the system design. But for each step, when you define it, you have to start to ask yourself, how do you evaluate or assess the success? And you have to define the testing criteria. You have to define the testing, scenarios. So basically, for the functional parts, for instance, from the code, you do the unit test, the integration test, the system test. These are more, we call these verifications. You have to think about, did I do the things correctly? That is something, developer can more or less be responsible. But the difficult part is this part, acceptance testing. You also have to talk to the customer to find out, are you doing the correct things? Instead of doing, the correct things based on the requirement. Yeah. The second ones, to assess if you are doing correct things is really challenging. And there actually get lots of, problem. If customer find that you spend 6 months or 1 year, you develop a completely useless things, what can you do? Yeah. And then that's why people invent, different alternative to fix it. Spiral model is one way. The way is, they add this kind of, risk analysis, basically in each iterations or each circles. They continuously, they start from some kind of, analysis of the objective, and then analyze the risks from the previous iteration, and then do the coding, and then finally, do this kind of planning for the next phases. So this is a very nice model, but the problem is in a software, in the software industry, in the literature we hear a lot, but in practice, it's quite difficult to apply. It needs a really experienced engineer or manager to guide all these steps. So actually people made lots of, alternative about spiral model. And one of them is called iterative model. So that's basically, make this life cycle much shorter, but still each one follows this, waterfalls. Instead of make a one waterfall model for 2 years, we do this like 1 month or 3 months. And then if one finished, and then we'll start the second one, and then third one. It's just like, you develop complex products, like, what you see here, these pictures. This is your final product. You can always start from simple ones. And then you talk to customer to show, well, this is our prototype. Do you like it? If the customer said, no, I don't, and then you get feedback. So immediately you fix them. And then you check with them again. And then with third iteration, you slowly get close to what user wants. So this actually becomes more popular in the software industry. And also we see in the in the development in the like research infrastructures, we typically apply this or see this in the use case development. And the agile models basically is a kind of practice people start to build based on an iterative model. If you look at the software evolution, basically you have different deployment. At each phase of the deployment, you have to define certain actions there to make sure the user feedback are ingested, and you can respond to that, make a plan, to respond to these changing requirements, make a development, and then test it and feed these to the next phases. So that is so-called agile. Still sounds very abstract, isn't it? When I teach this, to our own student in the software engineering, indeed, if you don't have the practice, you often feel it's a bit, abstract. But I have one more slide to help you understand more concrete. Think all these discussions from another directions. If at this moment you're not the developer anymore, you are a kind of a customer. You have such amount of money. You want to ask somebody to develop things for you. Think in that way. And you have a list of the features. You're thinking you want to deliver that. And you talk to the developer, say, hey, this is I want. I have a deadline. And I want to finish this within like 6 months, deliver it with this amount of money. Can you do that? If you use the classical way, normally you would do this. This is the list of the feature I don't want to change. Yeah, you cannot change that. But just tell me how much time you need, how much money you need. You give these, a developer to decide. In the classical way, if you work in this model, the risk is basically what we saw in the previous slides. The developers can always say, well, based on this list of feature, we didn't know the second feature is so hard. We need more time, and you have to give us, more budget. So basically, that is the classical model's problem. In a new model, agile way, if you are the, investor, funding agencies, or customer, you have to turn the things upside down. Thinking in other ways, there are two things, you don't want to change because this amount of money, this is the sense, it's fixed. Amount of time is also fixed. And within this timeline and the budget, because you have a hard deadline to deliver something to demonstrate your idea. But how the ideas are implemented, with the 10 perfect quality features or 11 less quality features or, other combinations, which is optional. Then, you could ask the developer, say, hi, this is my vision. I give you just a vision. Make a choice for me, deliver a number of features. And then you make a feature list tunable. So that basically, it's a kind of new mindset to give you better understand why agile, is needed. And we try to, apply this, actually start from ENVRI Plus project in the data for science team in the second part. And we see, how can we apply this in the agile use cases and to do these, reference model guided engineering. You can find a chapter in that book. It's chapter, I think it's 5 or 6, if I remember correctly. It's called reference model guided engineering. We explained in more detail about the challenges and the choice of why we select this method and how did we build interaction with different development teams from infrastructures. So agile, it's kind of general term. Agile itself has many specific approach to implement. It's just like a big umbrella. They have many, small techniques underneath. You heard probably some of them, in Lifewatch, we hear a lot because our colleagues in Spain, they are really like Kanban methods. And, some developers, in Amsterdam, we meet, they do like this extreme programming a lot. And Scrum is a kind of, more often used things. There was there is a statistics. So, and there was a survey, I think it's published 2 years ago. They checked these big companies and how these different agile methods are applied. And turns out, more than half of them are using, Scrum. Scrum is basically a kind of management methods to manage the processes, to manage the interaction in development teams, make sure, they respond to certain requirements, to the changing requirements or the new features, and in a very fast and efficient way. Yeah. So I use a few slides, briefly give you explanation as to how Scrum works. Maybe you can also try, in your own team. if you, have more colleagues, you want to work together as kind of agile team, you can try. It's very interesting how it works. Basically, you have different roles. You can make sure if you are a single person, of course, it's a bit difficult. You have to, activate as many things by yourself. Otherwise, you would think, the team has one person act as a product owner. This is a person understands what the final software look like, and he can, help you shape the features. And then we have a Scrum Master, and this is one basically manage the processes and make sure, the interactions move smoothly. And the development teams, basically, those are the developers, programmers, and then you need some kind of backlogs, to track all the current progress, and also user stories, sprint, backlogs, and burn down charts. So all these terminologies, I will explain you what do they mean. So it's like this. These are the three roles. So product owner basically is the one maintain the kind of product backlog. You can see this as a kind of roadmap, because he's the one knows, okay, in the coming 1 year or 2 years, as an infrastructure, I want to deliver this set of features. And then he is also the one talk to the customers to collect these kind of user stories. User stories, something like, as a scientific workflow developer, I need a kind of, cloud-enabled engine so that I can run workflows. So this is a typical pattern you structure user stories. You can collect lots of them. Why you collect them? Because, soon after you get this and you digest it, make a list. What are the prioritized ones? And then you talk back to the team members. And then this guy, Scrum Master, together with you, start to chunk, the objective or the products you want to deliver in the next phase into smaller pieces, which we call sprint. Typically, sprint, it takes like 1 to 3 weeks. It can be short, it can be long. It's highly customizable. It's based on your practice. For each sprint, you build some kind of phases. For instance, you can make a planning phase, like a few days, building phase, testing phase, and review phase. And then you write all this down in a kind of system, as a kind of backlog. You track it. It's a big table. And the planning table, basically, a planning meeting is really at the time you make agreement. It's very important. The agreement is some kind of sense. Everybody think this is our urgent or prioritized things. Everybody have to contribute. And then you move to the next phase, since start to execute. Developers start to pick the tasks from the backlog, execute it, implement it. And then you have to organize a kind of daily meeting to talk to each developers, make sure they behave properly. Ask them, what did you do yesterday? What will you do today? And do you face any difficulties, obstacles? Actually, we tried these methods in a reference model development teams. We started from that scenario. It works really well, especially make all these team members, at least make everyone work. Because if you don't work, you have problem to report every day. And then the system basically try to make a kind of burn chart to make sure the one you delivered, how what's the percentage you approach the total list of the feature you promised for that specific sprint. And then you make a kind of review meetings at the end of each sprint to make sure the current sprint, all the progress is on plan. And if there is anything you didn't meet the plan and you have to find out why, can you avoid that in the next phase? What will be the strategies, etc. So that is more or less like how the Scrum workflow works. So it is kind of since this the winter school is rather short. Usually in our own software engineering program, we encourage the students spend more than 1 month. It's half of the course. Basically, they have to form their own Scrum teams, work on certain projects to practice these roles. And in our case, I would encourage the students, you team up, and then during the break, in the next hour in the kind of interaction time, try to apply some of these methods, share some practices. Maybe some of you are already using this in your daily work. If not, you can practice a bit. Now we talked about these agile directions, how this is managed. Let's take a look at the other directions, the continuous delivery integration testing part, how that works. So basically, this is the work more, get the input from the developer back to the operational environment. So think about the developers, context. They are teams, and they work all with their own computer. Everyone produce some kind of code, in their daily activities. So basically, they all have kind of, version control systems. The thing is, everybody, of course, produce code in different qualities. How can we make sure, their codes are, can be integrated in certain quality, which we can release as a production service? And there actually, you can think again, this V-shaped model. We also, use a lot in the software engineering projects and try to define these roles. For instance, in the coding part, it's responsibility for the developer. They have to do the unit test. Unit test is, check the code which the person develops and make sure it delivers, the features it wants. It's a bit more than debugging. Debugging is the sense is before you do the test. If the code is buggy, which means it doesn't work, isn't it? So when the code starts to work, you have to test the code as a white box, give certain input, and you check the output, make sure the output meets what you expected. And when the unit test is finished, and then you start to move to the next phase, which we call integration test. Integration test, you put your component with the other people's components, and then to see if these, system as a whole, with different modules, you give them a certain input. Does the output looks like, what you expected or not? And then a system test, you make some kind of, test together with the more close to the operational environment, that kind of settings, and see the performance, see the scalabilities, finally do the acceptance test. So you can see actually up to this point, system testing, lots of things, you could actually automate it. Because, if you understand the specification from the requirement, which means you more or less know the output for a specific input, you know the expected output. So if you specify those two things and give this to another software, that software basically, is just for testing. That software can take your input, send this to the code you developed, and then observe the output and then compare them, and then see, if they match or not. That's the basic scenario for doing the testing. But actually, software testing is slightly more complex than that. But if you want to simplify it, that's more or less the scenario. The thing is, in software, software system. It's not like a physical system. Software, it's not a continuous system, which means if you find a bug, if you find a problem, for instance, I found a certain input doesn't meet my expected output. It doesn't mean for that particular input I can extend one variable a bit, I can find extra bugs. It's not always the case. Actually, in many cases, it's not the case at all. So all these kind of problem points are basically scattered randomly. You have to, apply certain, automated way to scan all of them if you want to fix or detect all these, problems. That is another motivation why we did automated testing. So automated testing basically seems like work like this. We are the developers, through some kind of, open version control systems. Everyone, start to commit code. From their version control system, if the new code is committed, basically you send a kind of events to trigger certain, process. So this process will be start. You just take your input, what you committed, and then build it, and then start the testing procedure, and then try different input and see how the output look like. And if all this finished, and then basically what that new commitment has to be put it back together with lots of pre-existing components to see as an entire system if that works or not. If yes, and then you basically make a new release, and that new release will be sent to the operation environment. And that basically, if it's fully automated, that's what we call continuous, testing, integration, and deployment. And in this context, actually, you can see cloud actually, have two important places, to help us. One is, in this testing pipeline. Remember, if the team, is very big, we have many developers, which means the test pipelines basically will be activated or will be triggered per event. There will basically be many instances of the pipelines. They all do the testing, and then they consume resource. And if you only have a small fixed size machine, it's very difficult to do that. If you want to support the bigger teams, cloud first, you need it here. Second, of course, for the operational environment, you also need cloud because the service instances, will be deployed there. And if the number of user increases, you also want to monitor, these quality of services and to decide, do you want to scale the service out or scale them up? So this basically is another way. So these are the monitoring and adaptation part. So in the, if you put all these, things together in the software pipelines, we can see, in the terminology we call continuous integration, more or less, service builder to the software testing. That is more or less in a continuous integration process. Delivery is end up here. And delivery, of course, at the end, there is a kind of decision making. Usually in the big companies, there is always kind of, a small committee and to decide, is this feature, is this feature need to be delivered in this, week or, next week or even next season. Basically, they better understand, their customer, how to do that. And there are lots of technologies, and these are a list of examples. Some of them maybe you are familiar with. Like Travis, this is closely integrated with GitLab environment, and there are also other things. So Jenkins is one of them. Actually, in our lab tutorial, we're going to try to show you how Jenkins can be used to set up your own pipeline to manage these continuous integration, testing, and deployment. So from public cloud providers, they also have their own solutions. For instance, Azure has one, and this AWS has, EOS actually has one called Gelastic. In the early adopter program we got from EOS project. So actually we have a team. Basically we investigate these different DevOps solutions. And we hope, that part, we will come up with a kind of white paper to summarize the practice we learned and share that with ENVRI communities. So in the part for the Jenkins, what we're going to do is basically we set up these basic steps. We put them in a document. It's more like a tutorial. And if you followed it, in principle, you will be able to have your own automated pipeline. You could try this on the virtual machines you get from the course. By the way, I still need to figure it out with Nicola, how are we going to distribute these virtual machines to all of you. So you can try to deploy this in there, or you can just even try this on your own, virtual machines, if you already have one and in your own environment. And at the end of this, in the document, actually, we embed some questions. At the end, also provide some kind of discussion questions for you. You can think about, for instance, if the performance drops in this pipeline, what can you think of, to improve that, etc. So that more or less reached the end of my of the lecture. So since we started a bit late, also time is a bit short, I will just move a bit quicker. Leave the discussion at the end. Is that okay? So let's have a quick summary about what we discussed. So first we discussed, in the first part, we discussed how to run an application in cloud. So this is the basic pipeline. You do the infrastructure planning, containerization, deployment on the Docker cluster, and then monitoring. So the Docker basically is another piece of technology you need in mind. And we discussed different options and compare them even a bit. So I think you can think about in your own working scenarios and see if you can select the best choice for yourself. Second, we also discussed the the software development and operation life cycles, and discussed why for the services we need to have these kind of business viewpoints on the service, and to understand why we need agile, why continuous integration, testing, deployment is important, and what are the technology we can apply to deliver these kind of agile and continuous integration deployment. We also argued why cloud is important there, and finally, we prepared 3 lab assignments for you. So the first one is for the first part, and then we have this. We focus on the containerization, publishing Docker, and set up Kubernetes. That's for the first tutorial. Second is this, run the Docker on a Kubernetes environment. And third tutorial, it's about Jenkins and to set up your own open source DevOps. But be aware, so the DevOps is a practice. It's not, there is no real standards to say, well, this pipeline is DevOps, that one is not. We don't really have this kind of distinguish. It's more about the practice. If something is really matches your needs, that probably is the best for you. But these technologies, it's up to you to decide how to combine them, how to integrate them. I also put a link here, which is the assignment we provided in the summer webinar. There actually we give some extra information about REST service. How do you build a REST services and how to containerize that REST service and how to deploy it in the Kubernetes. If you are interested or if you want to know more about how REST service develop, you can also take a look there. Yeah. So these are the lab assignments. So yes, so I would leave the last few minutes before we start the discussion part in Wonder Systems. I want to have some discussion with you if you have questions or not, or what do you think about these two topics we discussed? Are there anything you think it's not clear? Anything, please feel free. Just give me some feedbacks.
Yeah, I have some thoughts
Yes.
about this lesson, and like generally speaking, I feel that so all of these topics, on one hand, you can really appreciate them. For example, the first part, if you have already taken place um, into the process of resources application for your own work. And the second part, I guess, people that have already been involved into code development and release, I guess they will be more familiar, and it would be easier to follow for such targeting audience. Generally speaking, but like I guess the nice part is that even for people unfamiliar with all of it, it's nice that you have all of these information wrapped up in a lesson one after another. So even if you might not be able to directly contribute and give feedback right now, because all of those information, they take experience and time to process and digest.
Yep.
From what little experience I also have, so that is understandable. But I guess it's still useful to have them in one place, also with with the chance to give to deepen the knowledge with tutorials and such. That's one. But I also have another question.
Yeah.
Which is about the orchestration part.
Yeah.
Okay. So I am in a situation in which I might need to ask for cloud computational resources.
Mm-hmm.
And as such, I would need to basically set everything in a containerized fashion with Docker or Singularity. And I really wanted to understand the importance of the orchestration, for example, with Kubernetes, as you said before, by setting all of these pods. Okay, why is that important? Why do
Yep.
I just not? Why can I just not use a single container, single Docker?
Yeah.
That's it.
It's really depends on the types of interactions you need. So right. We use a lot about those things when you want to customize the networks, to customize the interactions between those specific sets of the containers to optimize their behavior. So let's say in many cases, I would say probably you don't need bother about it. If the container itself is relatively independent, the communications, file sharings are rather standard. You could just skip it, and I think your application will still work. But the thing is, if you have a workflow, some tasks you would like them just work close to each other. You don't want the orchestrator split it, send it to completely different nodes in the cluster. If you want to put them together as close as possible, then you need do these kind of things by yourself, or at least tell the orchestrator, hey, these are the things, please group them. And this also you basically do this through practice. When you face certain problem, you start to look up these technologies and then to see if they can solve it. There is very good documents from Docker explains how all these things works. You can also take a look there. Sometimes, understand these technical options first before you do the implementation can save lots of effort.
Of course, yeah,
Yes.
yeah. If you start from the check how feasible your things are. Yeah, I guess that helps. And so, for example, if my pipeline is based on MPI,
Yes.
okay, I guess that might be the case where I would need to be interested into this orchestration stuff, right?
That's one. And also you have to be aware, I think if you're really using MPI is supposed to do high performance job. Basically these types of workloads, it's really communication, let's say it's latency sensitive. Whether you would like to do this really through Docker or you just do this on a plain set of the VMs, set them as a kind of MPI cluster, probably the second choice is better for you.
Yeah. Yeah, of course.
Yeah, because MPI job is more or less what we call standalone application, but they do forks that generate processes at runtime, isn't it? Yeah. If you tell this system how many VMs is available in the cluster for the MPI job, MPI actually manage the things, also very nice for you. If you leave this to the Docker, basically add one extra layer there.
Yeah, and that's what the orchestration part does, right? That's what you said before.
Yeah, the orchestration part, actually they have a current orchestrator, they don't really have the knowledge how to handle this MPI job. You have to do this lots of things by yourself. Orchestration in the container was not designed for MPI types of workload.
Okay. That's some food for thoughts. Thank you.
So any other questions or remarks? So
I have a question, Jimmy.
Yes.
Yeah, so this is Maggie. So you were touching on, especially in the second lecture about how important it is to always be in contact and have good communication with the end users of your service or your product. So I was thinking that this can sometimes be, I think, a bit of a challenge for research infrastructures because it's maybe not completely clear from the beginning who these end users are. And also, even if you do know that more or less clearly, how do you actually engage in this communication? Should you have user groups or should you have a focus group or just individual contacts? Can you comment on that?
Yes, I think to me, this focus group itself, it's already a kind of step towards this, user engagement, because from there, with different inputs, some of them probably already represent certain kind of potential user of your services, their opinions and their ideas. If that can be well digested in these, focus group or, task forces, I think that can be a very valuable input for what we call product manager to decide what's the direction to go. That's one comment. Secondly, I think why in the research infrastructure, we talk a lot about use cases. If you're building something, it's so difficult to find the use cases. Probably you need to think about, is these things really urgently need or not? To me, all the technologies, especially in this data science or research infrastructure, in principle, they should, we should be able to find a kind of use case, to assess it, to demonstrate the potential. Of course, it's not always true in the industrial innovations. You have some kind of disrupt technologies. You don't have use case at all in the beginning. But in the research infrastructures, probably these are not really a kind of common case. We should push ourselves a bit, think about the use case. By doing that thinking, you will start to, reach different potential users or stakeholders, and then, to find out who are the, first, trier of your final product. But it's still very difficult indeed. I mean, Maggie, you touched this issue. I think all the research infrastructures are facing. We don't have a good answer to that. We can only try. We have tried a lot of things, but we don't think, at least in the ENVRI process, I don't think we have really have a good answer to that. Use case probably is one of the best practice I think we can share.
But to me, a use case is useful during development or sort of setting up an architecture that could potentially manage the typical cases. But I'm more concerned about once the service is actually there. How do you do a proper service evaluation, and not only from the purely hardware or software points of view, but really the features. How do you set up a system that which welcomes participation of end users in sort of further developing, and of course also catching errors and problems?
That's more like the validations. Hackathons is one of the ways people try a lot. We see in the different infrastructures. They invite young researchers, really with the open-minded, and then offer them free data sets, give them infrastructure, and then those surface as a tool, and just give them a few days and give them very simple tutorial on how to use these, and then make this as a challenge. Actually, we'll find lots of interesting output. Basically, these young researchers are more, more crazy. They have more open-minded. They can more find ways how to use these, services. It's for the mature scientists. I think they are more experienced, but on the other hand, they are more educated on some kind of, methodologies or tool sets. Probably, we should think of in the infrastructure, in the research infrastructure context. Try both. The community workshops target to the mature scientists, but young scientists, starters, we should really encourage them, try those things, help us identify the potential passes.
Okay, thank you.
You're welcome. Are there any other questions? If not, Nicola, are you in the call?
No.
Lucia, it's one question for you. So for the lab part, I know you or Nicola created a couple of virtual machines for us. The thing is, I'm not sure, I didn't get the entire list. For the tutorial, the students needs to, to get access to them. At least every 2 students should get 1 VM. How are we going to organize those, user accounts?
Yes, Nicola prepared, I'm seeing the list, 12 machines at the end. And the user and password are the same that he sent to you. And the addresses, I can put it here for you in the chat.
Right, but he only sent me 1 machine. I don't have the other 11 machines.
Okay. No, we have 12, not 20.
12. Then in that case, we have to divide it in such a way that every 3 students need share 1 machine.
Yeah, we can divide students.
Yeah, I mean, last time we tried it from EGI. But and also, can you tell us how long student can keep those virtual machines?
Okay. Yeah, he told me to say that you could explain that they can use it via SSH by means of the IP address and credentials that I put here in the chat.
But my question is, how long can they keep the VMs? For instance, like 1 week, or these VM will be destroyed after the winter score immediately?
No, I think that they can keep it at least for 1 week in order to test, in order to.
Yes, so that's very important. Okay.
Yes.
So if you said you send the links in the chat box, but that's just 1 IP address. I'm talking about these 12 machines. Where are they?
No, he sent me only the list of IP. So here and others.
So let's do like this. We will figure it out how to allocate those VMs to the students. Yeah. Maybe we can stop the lecture now, and people can still feel free to go to this social platform to do the interactions. Yeah, my colleague, I think Ricardo is here, and Spiros might also be here. I think they can also join the discussion in the social platforms. If you have questions, specific questions about cloud computing technologies, try to find these two colleagues and ask questions. So Lucia and me, we're going to figure out how to allocate them and notify you through the training platform. Is that okay?
Okay, perfect.